Hey y'all, this is the 6.1 notes over sequences. A sequence is an ordered list of numbers. Each number in the sequence is known as a term. Each term of the sequence is a function of its position. To define a sequence, a formula for the nth term must be given. An explicit formula gives the nth term as a sub n, as a function of n. So it starts off easy. It asks us to find the next four terms in each sequence. So again, the sequence is just a list of numbers with some type of order, some type of pattern. So we just have to figure out what this pattern is. And if I look at this, I see, well, it's just dividing by 2 every time, right? Half of 32 is 16, half of 16 is 8, half of 8 is 4. So if I were to keep going, the next term would be half of 4, which is 2. Next term would be half of 2, which is 1. Next term would be half of that, which is 1/2. And next term would be half of a half, which would be 1/4. And we could go on with this forever, but it just asked us for the next four. The next one, it's a little bit harder to see, but you might look at it a while and see that, well, from here, it adds 1 to get from 1 to 2. From 2 to 4, it added 2. From 4 to 7, it added 3. There it added 4. Then 5. Then, oh my goodness, then 6. To get our next one, we're going to add 7, which would get us to 29. To get our next one, we'll add 8, which would put us at 37. To get our next one, we'll add 9, 46. And to get the last one that we need, we'll add 10, 56. Okay? Then find the first four terms of the sequence given by a sub n equals 2n times -1 to the n. So this is an explicit formula, like it told us up here, because for an explicit formula, I can just plug in n. I can say I want to know the second term, or whatever it may be, and I plug it into the formula and get my answer. So if I want the first four terms, the first term is always at position 1. So I'm going to plug in a 1 to get my answer. So a sub 1 equals 2 times 1 times -1 to the 1. Then I evaluate -1 to the first power. Well, anything to the first power is itself, so that's just -1. And 2 times 1 times -1 would give me -2. Okay, second term would be a sub 2. So let's plug in 2 for n. 2 times 2 times -1 to the second power. So again, PEMDAS says do our exponents first. -1 squared means -1 times -1. That would give us a +1. +1 times 2 gives us +4. For a sub 3, I'm going to plug in a 3. 2 times 3 times -1 to the third. -1 to the third power would be a negative. If I have an odd power, it's going to stay negative. -1 times 3 times 2 is -6. And the last one it asks us to do, let's get the fourth term. 2 times 4 times -1 to the fourth. -1 to the fourth would be +1. 2 times 4 times 1 is +8. So our first four terms of that are -2, 4, -6, 8. Cool. Whoa. Okay, so remember that was an explicit formula because I just plugged in the place I want and got my answer. We can also define sequences recursively. Recursively defined sequences give one or more of the first few terms and then define the terms that follow using previous terms. So there is a formula that uses a previous term. So we can't just plug in any number we want because we have to know the previous terms. We have to go in order. So like on number 3, it asks us to find the fifth term of the recursive sequence. It tells us a sub 1 is 1, and then it gives us a formula, and it says that formula works everywhere where n is greater than or equal to 2. So to get the fifth term, I have to work my way up to it. I can't just plug in a 5. So I'm going to start with a sub 1, which is going to be easy because it already told me what that is. A sub 1 is 1. Great. Let's find a sub 2, meaning let's find the second term in this sequence. And to figure that out, I'm going to plug that in to this formula right here. Instead of all my n's, I'm going to put a 2. So a sub 2 equals a sub 2 minus 1 plus 2 times 2 minus 1. Okay, well, let's take this one step at a time. Let's deal with this a sub 2 minus 1. I know what 2 minus 1 is, that's just 1. So that's the same thing as a sub 1. And I'll just write the rest of this out. So what this is saying is plug in a sub 1, meaning plug in your very first term. And we know, because it told us in the problem, that a sub 1 is 1. So instead of a sub 1, I'm going to put 1. Now it's just an easy algebra problem, right? 2 times 2 is 4, plus 1 is 5, minus 1 takes me back to 4. 4 would be my answer for a sub 2. Let's find a sub 3. We'll do the same process. We're going to plug 3 in for all the n's in this formula. So a sub 3 equals a sub 3 minus 1 plus 2 times 3 minus 1. So a sub 3 equals a sub 2 plus 2 times 3 minus 1. Now this one calls on a sub 2, which is the one we just found. We just found out that a sub 2, our second term, is 4. So I'm going to plug in a 4 into this formula. So 4 plus 6 minus 1, which gives me an answer of 9. To get a sub 4, I'm going to use that same formula again. A sub 4 minus 1 plus 2 times 4 minus 1. A sub 4 equals a sub 3 plus 8 minus 1. A sub 3 we just figured out was 9. So 9 plus 8 minus 1, which gives us 16. Finally, we're ready to figure out what our answer is. We only needed the fifth term, but in order to get to the fifth term, we had to go through all of these because it was a recursive formula. So let's do a sub 5. A sub 5 equals a sub 5 minus 1 plus 2 times 5 minus 1, which would be the same thing as a sub 4 plus 10 minus 1. A sub 4, that's what we found out right here, is 16. 16 plus 10 minus 1. Combine all those together, we finally get our answer of 25. So recursive formulas are a little bit more work, but they're not bad. It's just using the term that you already found. You have to go in order and find them all. So on number 4, when it says find the sixth term of the recursive sequence, a sub 1 equals 3, a sub n equals negative 2, a sub n minus 1, we've got to plug in 1, 2, 3, 4, 5, and then finally we'll get to 6. But this one's actually not as bad as the one we just did. So it tells us a sub 1 is 3. That's a good starting spot. To figure out a sub 2, we're going to plug that in to this formula. So instead of n, we're going to put 2. So negative 2 times a sub 2 minus 1, which is negative 2 times a sub 1. Well, a sub 1 is 3. Negative 2 times 3, which gives me an answer of negative 6. Okay, a sub 3 would be negative 2 times a sub 3 minus 1. A sub 3 minus 1 is a sub 2, which is what we just found, negative 6. So I'm going to plug in a negative 6 to get an answer of positive 12. A sub 4 equals negative 2, a sub 4 minus 1, which is a sub 3, which is what we just found, is 12, equals negative 2 times 12, which is negative 24. a sub 5 equals negative 2a sub 5 minus 1, which is a sub 4, which is what we just found. Negative 2 times negative 24, which gives us positive 48. And then finally, to get a sub 6, which is what we wanted from the beginning, negative 2 times a sub 6 minus 1. A sub 6 minus 1 is a sub 5, which is what we just figured out is 48. Negative 2 times 48 gives us a final answer of negative 96. That would be the 6th term of this sequence. All right, now comes my favorite part. We're going to talk about factorials. I like factorials a lot. It's going to seem a little weird, maybe. But factorials come up a lot in probability and statistics. So a factorial looks like an exclamation point. I mean, it is the same symbol, but in math, what it means is that whatever you are taking the factorial of, so if you have n factorial, you're going to multiply n by every integer below it all the way down to 1. So for example, if I asked what is 4 factorial, the answer would be 4 times 3 times 2 times 1, because it's every integer below 4. And then if I actually multiplied those out, I would get 24. So on number 5, where it says 6 factorial, well, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. And if I were to multiply all that out, let's see, 6 times 5 is 30. 30 times 4 is 120. 120 times 3 is 360. 360 times 2 is 720. Times 1 is still 720. So 6 factorial simplifies to 720. Okay, number 6. Okay, what would make factorials more fun than adding fractions? So let's add fractions. 12 factorial over 10 factorial. Okay, I know this problem looks scary. It's really not bad because so we know what factorial is, right? I'm multiplying by every integer below. So 12 factorial would be 12. Let me draw my fraction. 12 times 11 times 10, etc., etc., etc. Another way I could say that, isn't that the same thing as 12 times 11 times 10 factorial? Because I'm saying I'm going to keep multiplying that 10 by its integers. So 12 factorial is the same thing as 12 times 11 times 10 factorial. And the reason I did that is because I have 10 factorial in the denominator. And I want to cancel those out. And that just made life a lot simpler. That's a lot less multiplying and dividing we're going to have to do because we were able to just cancel that out. And then I can just multiply 12 times 11, which would be 132. Okay, last one. Let's add some variables in here. Right, so the way these factorials work doesn't change if I'm looking at variables, right? Because, for example, on this 12 factorial, we could have thought about this as this is 12 factorial, 12 times 12 minus 1 times 12 minus 2 times 12 minus 3 times 12 minus 4, etc., until we got down to 1. Well, the same thing is true here. We're just subtracting 1 and multiplying. So, just as a side note, n plus 1 factorial would be the same thing as n plus 1 times n, because n is 1 less than n plus 1, times n minus 1 times n minus 2, etc., 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 all the way down to 1, whatever that happened to be. I don't know because I don't know what n is, but that's the way the factorial would work, right? I would just keep multiplying by a number 1 less. So another way I could write this numerator, instead of n plus 1 factorial, I could say n plus 1 times n factorial, right? Because I could say it's this times this factorial and not have to write that, etc., etc., etc. And again, the reason I would stop right there is because then those n's cancel out and leaves me with my simplified answer, n plus 1. Yeah, so that's our last example. Factorials are fun. You don't have to believe me yet, but you'll get there, I hope. Ask questions if you have them, guys. Good luck. You got this.